Now we will discuss importance of electron affinity. Importance of electron affinity, that is EA. As we know that electron affinity means tendency of electron accepting by the associated gaseous atoms. For example, X is the gaseous atom accepting one electron and convert it into X negative. In this overall process, energy is released, which is called electron affinity, where E becomes electron affinity. Now we will discuss about importance of EA. First is the elements having higher value of EA. Now first is elements having higher value of EA act as strong oxidizing agent. Strong oxidizing agent. For example, oxygen, fluorine, chlorine, nitrogen, bromine, etc. These elements act as a strong oxidizing agent. Since these elements have a strong tendency, second one is since EA decreased down the group, it's a group behavior, and EA increased left to right in a period. It's a period. So down the group, electron gaining tendency increases. It means oxidizing power. It means non-metallic character. Non-metallic character increases. And similarly, in a period left to right, EA increases means non-metallic character. Non-metallic character increases. That's why in the periodic table, right hand side element non-metallic, and the left hand side element will be metallic. Third one is we'll be discussing about reducing nature. Then it will be decreases in a period. So in a period left to right, this behavior becomes, that is reducing nature becomes decreases. So element placed right hand side will be less reducing agent, and left hand side will be strong reducing agent. It means metals is a strong reducing agent. Metals is a strong reducing agent. Now we will discuss about next periodic property, that is called electron negativity. En. It means electron negativity. Electron negativity, it is the property of any atom. It is the property of any atom. The relative tendency of an atom to attract the shared electron pair towards itself is called electron negativity. For example, if we have taken an example like HCl, in HCl there is a covalent bond between H and Cl, and this covalent bond formed by the sharing of one electron of H and the one electron of Cl. Cl form covalent bond with the hydrogen bond to complete its octet. And after the sharing of electron, Cl have 8 electrons in the last orbit. Similarly, in this case, hydrogen complete their octet. Since hydrogen have only 1 electron, so after sharing with Cl, complete its duplet. Now what happens after sharing? After sharing, this shared electron, this one is also called bond pair. This shared electron or bond pair is more shifted towards Cl. Means after sharing, this bond pair shifted 70% towards Cl and 30% towards H. So here is the partial negative charge developed on the Cl and partial positive charge developed on the H, which is represented by delta negative and delta positive. And now after sharing, the HCl molecule is considered as a dipolar molecule. So in this molecule, the tendency of Cl by which it attracts the electrons of hydrogen towards itself, which called its electron negativity. So here is that we can say that electron negativity means electron attracting power of the Cl is greater than H. Similarly, if we have taken another example, for example, if we have taken a molecule that is FCl or ClF. In this example, bond between Cl and F again formed by the sharing of 1 electron would complete the octet of both Cl and F. But after sharing of this electron, there is a development of partially negative and positive charge. In this example, here is the Cl is partially positively charged, but F is partially negatively charged. So in this example, this bond pair or shared electron is more nearer to the F as compared to Cl. Means electron attracting power of F is greater than Cl. So we can say in that case F is more electronegative than Cl. And in this example, Cl is more electronegative as compared to H. The second example is Cl is less electronegative than F. So when we discuss about electronegativity, it has been clear that En is always found out in the comparative term. It can be never found individually. For example, if we found the individual En of Cl, then according to first example, Cl is more electronegative. But according to second example, Cl is less electronegative. So how we can say that what is the exact electronegativity of Cl? That's why Cl is always formed as a comparative term and it is always found in the covalent form. Now we will discuss about the basic difference between Ea and En. So Ea and En. Since we have already discussed that Ea means an isolated gaseous atom except 1 electron, then it will be converted into X negative ions. When that process energy is released, which is called Ea. So here is the basically Ea means the energy which is liberated in the electron gaining process. So we can say that this is a exothermic reaction. And in this exothermic reaction or exothermic process, energy which is liberated, that is called Ea. But if we have discussed about En, then what about En? En always found in the compare term, and if we have the example of the HCl, then we can see that Cl is delta negative, H is delta positive, then En of the Cl is greater than H. So it has been clear by the help of both examples that Ea is calculated by the of any individual atom, but En is never calculated in the individual atom. It is always calculated in the compared term. And second one is Ea have a unit. Now, what unit about Ea? Basically, Ea means energy. So, unit which is responsible for the energy is also the unit for Ea. For example, kilocalorie per mole, that is the unit of Ea. But as we know that En is always found out in terms of compare. Hence there is no unit of the En, since it is always found in the comparatively. So here is the basic difference between E and En. Now we will discuss about periodicity in En. We discuss En in a group. First, what happens in a group? As we know that in a group from up to down, that one is the representation of a group. As we know that in a group, radii becomes increases. It means there is a more difference between nucleus and outermost electron. And we know that electronegativity means the electron attracting power of that particular atom. And basically in the atom, electron attracting power is shown by its nucleus, since nucleus is positively charged. So if the size of the atom is already larger, then there is a large difference between nucleus and electrons. In that case, if another electron comes in contact to that nucleus, then comparatively there is a small attraction force of that electron by that nucleus. So we can see that down the group, when radii increases, the attraction force of a nucleus decreased on the excess electron. That's why En becomes decreases down the group. For example, if we have taken an example of simple first group element like lithium, sodium, potassium, rubidium, cesium and francium, that francium is a radioactive element. Now, this first group, when we down the group, the radii becomes increases, means the stable elements, cesium is the largest atom and it has the least En. So in the periodic table, least En becomes cesium. Similarly, we have discussed about halogens, that is group 17, that becomes fluorine, chlorine, bromine, iodine and astatine. Here is the astatine again, radioactive element. So in this group, down the group, radii increases, so En becomes decreases. So here is the fluorine is the most electronegative element. And in the periodic table, F is the most electronegative element. Most electronegative element. It means the least element becomes cesium and most electronegative element becomes fluorine. Now, if we have discussed the trends in a period, second one is period. If we discuss of the period of any period in the periodic table, then in the second period, there is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and the last is neon. Now, when we go from lithium to neon, there is a regular decrease of radii. So we can say that here is the En becomes increases, but here is the En increases from lithium to fluorine, but En of this inert gas or noble gas or rare gas is almost zero, since neon has stable electronic configuration, so it don't have any tendency of the electron attracting. So we can say that in a period lithium to fluorine, ENH continuously increases. That's why the most electronegative element of fluorine. And if we have discussed about radii, in the radii, again same trend, the radii becomes decreases from lithium to fluorine. But the radii of the neon is larger since in case of neon, the radii becomes van der Waals. It is not considered of a covalent radii. But lithium to fluorine, all elements have a covalent radii. So we can say that the strongest electronegative element is fluorine and the least electronegative element is cesium. And in the inert gases like helium, neon, argon, krypton, xenon and radon, these all gases have the value of En becomes 0 due to its stable electronic configuration, that is NH2 and P6. Only the helium have duplet. This is the electronic configuration of NH2. We have discussed some exceptions about En. Exceptions of En. If we discuss about group 13, that is boron family. The element is boron, aluminium, gallium, indium and thallium. And the group 14 that becomes called carbon family. It is carbon, silicon, germanium, tin and lead. According to general trend, we know that En decreases from up to down in a group. But in group 13, En decreases from boron to aluminium. It means En of the boron, it becomes 2.0 and aluminium becomes approximately 1.5. But after aluminium, there is no decrease of En, it will increase. Means En of gallium becomes 1.7. Here is the this change due to the presence of d orbital. The atomic number of aluminium becomes 13. The atomic number of aluminium becomes 13 and gallium becomes 31. In between 13 and 31, there is a one series of d block elements. The presence of d block elements and poor shielding of d orbital, the size of the aluminium and gallium is almost same, but there is a more attraction force in gallium as compared to aluminium. Its En is greater than aluminium. Similarly, if we have considered the En of carbon, it becomes 2.5 and the En of silicon down the group according to general trend it becomes 1.8, but En of the germanium is not down, it is again 1.8. So En of the silicon and germanium is almost same due to the same region. So here is the group 13 and group 14 elements shown the general trend of the En that shows up by the other groups in the periodic table. Now we have discussed some importance of En. On the basis of En data, we can predict something about nature of the bonds. For example, if the En difference between two elements, that is A and B, and their En difference becomes XA minus XB, it becomes equals to 0. Then in that case, bond becomes what? Purely ionic. Purely covalent. In that case, bond becomes purely covalent. And the second one is difference between Xa minus Xb is not 0. Then in that case, bond becomes polar covalent. Means compound have partially negatively and positively charged. Now, if we say that bond becomes polar covalent, then definitely here is the covalent bond have some ionic character. So, if the difference between Xa minus Xb is 1.7, then bond becomes 50% covalent and 50% ionic. And the next is if difference between Xa and Xb, that is En difference between Xa minus Xb greater than 1.7, then bond becomes what? That is 70% covalent, 70% covalent and 70% ionic. Since in that case En difference increases, so bond becomes 70% ionic and 30% covalent. And if the difference between En, that is Xa minus Xb is less than 1.7. Now in that case what happens? Bond becomes, in that case, bond becomes 70% ionic, 70% covalent and 30% ionic. So by the help of En or En difference, we can predict the nature of the bond